Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic, fabrication process of nMOS and CMOS. After completion of this topic, you will be able to illustrate the steps involved in fabrication of nMOS and CMOS transistor, and you will be able to differentiate between nMOS and CMOS fabrication steps. This represents the overall view of the 3D cross-section and front view of an nMOS transistor, what we are going to learn now. Fabrication process of nMOS. It consists of different steps where it starts with step 1. The process starts with a silicon substrate of high purity into which required p-type impurities are introduced, which is known as doping, lightly doped. So pictorial representation, you can see figure 1 is the plain silicon substrate without any impurities, and figure 2 represents the silicon substrate lightly doped with the p-type impurities. Step 2, a thick layer of silicon dioxide is deposited all over the surface of the substrate. This is for the purpose of protecting the surface during the processing of other layers. So compared to the previous step, so the silicon substrate after doping with lightly p-type impurities, then a thick layer of silicon dioxide of 1 micrometer thickness is deposited all over the surface. This acts as a protection. Step 3, the surface is covered with a photoresist and spun to achieve an even distribution throughout the wafer. Figure 4 represents the photoresist is deposited over the silicon dioxide layer. Step 4, the photoresist layer is exposed to ultraviolet light through a mask. This mask defines the region into which diffusion is to take place. Figure 5 represents the silicon substrate deposited with a thick silicon dioxide of 1 micrometer with a photoresist, and a mask is used to expose the substrate to the ultraviolet light. This is termed as mask 1. Step 5. Area under the mask is etched away together with silicon dioxide and photoresist. So whichever the area not exposed to ultraviolet light can be etched away together with the silicon dioxide and photoresist, whereas the remaining portion will be hardened and the thick silicon dioxide will be hardened in the other areas where the ultraviolet light is passed through the mask. Step 6. A thin layer of silicon dioxide is grown over the entire surface. You can look to the figure where a thin layer of silicon dioxide of thickness 0.1 micrometer is grown all over the surface. Then followed by step 7, a thin layer of polysilicon is grown over the entire surface to form the gate. From the figure you can see over the silicon substrate we have a patterned thick silicon dioxide, then followed by all over grown thin silicon dioxide, then followed by a polysilicon layer of 1 to 2 micrometer thickness. Followed by step 8. Now a mask termed as mask 2 is used to pattern polysilicon to form the gate. So only where we require the gate, only at that place polysilicon should be there. In the remaining portion of the wafer, the polysilicon should be etched away. So a mask will be used and the substrate will be exposed to ultraviolet light through this mask in order to form the polysilicon only at the gate. See now, only at the gate the polysilicon will be sustained and remaining all portions photoresist along with polysilicon and thin silicon dioxide layer has been etched away. Followed by step 9. Source and drain are formed by diffusing n-type impurities, heavily doped. Look to the figure, our substrate with silicon dioxide on either sides of the substrate and through a window which is forming the gate on either sides of the gate, source and drain are formed by diffusing n-type impurities, N plus and N plus. Then followed by step 10, thick silicon dioxide is grown all over and then masked with photoresist and etched to expose selected areas of gate, drain and source to make the connections. This step is we require only a portion of gate, source and drain to be available to the external world to make the connections. The remaining portion need to be covered with silicon dioxide. The silicon dioxide layer is formed and then a mask is used in order to etch only the regions of gate, source and drain and remaining portion of the substrate will be hardened with the silicon dioxide. Then followed by step 11, metallization. That is a metal, typically aluminium, is deposited over the whole surface, masked and etched to form the required connections. To make a required connection to the external world can be made only through metal contacts. So throughout the substrate, a metal layer has been deposited, then covered with a photoresist and with the help of mask and ultraviolet light, we can etch away all the metal and photoresist with the silicon dioxide except the regions of gate, source and drain. The final NMOS transistor's front cross-section view will look as shown in the below figure. Only the metal contacts at source, gate and drain and remaining portion of the device is covered with a silicon dioxide layer. Summary of NMOS fabrication process, you can have a quick look. Starts with a substrate, then followed by thick oxide and a photoresist with a mask and UV light to form a window in the oxide to define our transistor region, that is to form drain, source and gate, then followed by polysilicon, patterned polysilicon, then followed by source and drain diffusions, then followed by contacts other than the contacts remaining portion with silicon dioxide, then followed with the metallization and its patterning. And see what are all the different types of masks that are used in NMOS fabrication process. To summarize, processing takes place on a p-doped silicon crystal wafer on which a thick layer of silicon dioxide is grown first. Then mask 1 is used to pattern this thick layer of silicon dioxide to define the region where the transistor need to be formed, that is gate and source and drain areas to be formed. Then followed by a mask 2 will be used during the thin ox region where depletion mode devices are to be produced. Followed by mask 3, this is used for depositing the polysilicon and then patterning that using mask 3. Then followed by a step of diffusing n plus regions to form the source and drain. Then mask 4 is used to expose only those contact regions where source, gate and drain need to be exposed to the external world. And then followed by mask 5 is used during the metallization process and its patterning. And mask 6 we have not discussed in the fabrication of NMOS. It would be required for the step of overglassing the entire process. 3D view of an NMOS transistor looks like this, where this is the three-dimensional overview, where the lateral length indicates the channel length and its perpendicular dimension indicates the width of the transistor, then followed by gate, source and drain with metallization pattern and P substrate forms the body and its front view will look like this. Hope that's clear. And followed by CMOS fabrication. So very important fabrication process is nMOS fabrication. Why? Because nMOS fabrication forms the basis and it is the fundamental route towards any fabrication process. Only through few extra steps and masks we can do CMOS fabrication compared to nMOS. So we will be focusing on the extra steps and extra masks while summarizing this CMOS fabrication process. Basically, CMOS fabrication can be accomplished using either of the three technologies. One is N-well or P-well technology, one is twin well technology, and other is silicon on insulator technology. Among these methods, the P-well process is widely used in practice and the N-well process is also popular. Let us have a look at the steps of CMOS fabrication process very briefly, as if now we have completed the nMOS fabrication process. We are not going into all the details of the CMOS fabrication process. See, only this has been represented in four steps. All the steps are combined and represented in few steps, where you can have a look to step one, where you can understand. Basically, we take an CMOS fabrication means we require both NMOS transistor and a PMOS transistor. And just now we have completed for an NMOS transistor, we require a P substrate. That means for a PMOS transistor, we require an N substrate. So we start with one type of substrate, considering it as the N substrate, which will be useful in order to form a P device, that is PMOS. But in the same substrate, if we need to have an NMOS, there should be a P substrate also. The first thing is to form a P well. So how to form a P-well means a silicon dioxide layer will be deposited all over the substrate and then it is patterned using the mask and ultraviolet to form a window where an N device, an NMOS can be defined with its gate, source and drain, and that window will be heavily doped with P impurities, making a P well. This is called as a P well inside the N substrate. So here we will define the gate, drain and source of the NMOS, and in this region we will define the gate, source and drain of the PMOS, and then it is followed by a thin silicon dioxide and polysilicon patterning to form the gates of both the PMOS transistor and NMOS transistor. Then followed by, in order to make a P diffusion, we use a P plus mask, so that will be covering all other regions except the region where we require a P diffusion to be made. So P diffusion here makes this a complete PMOS transistor with the polysilicon P diffusion and P diffusion on either side. And after this step, a P plus mask, which is a negative type of mask compared to the previous mask, will be used, which will be covering all the portion of the substrate except where we require an N diffusion. So here forming the N diffusion in the P well will make a complete gate with N diffusion on either sides forming source and drain, making it a complete NMOS transistor. And whereas the intermediate steps are understandable, you can refer to nMOS fabrication process for the intermediate steps of the CMOS fabrication process. The P well acts as substrates for N devices, that is known within the parent N substrate, and provided that voltage polarity restrictions are observed, the two areas are electrically isolated. So the area which forms the PMOS and the area which forms the nMOS in CMOS are both electrically isolated. However, since there are no now in effect two substrates, so totally we have two substrates now. One is a parent N substrate and one is a P well acting as a P substrate to nMOS transistor. Two substrate connections are required as shown in the figure. So you can look to the figure, two substrate connections, one forms. See, this is what our CMOS inverter circuit like. Both the gates are interconnected to form an input voltage, and both the drains are interconnected to form the output voltage, and source of PMOS is connected to the body of the transistor and is connected to the supply, that is VDD. And source of nMOS is connected to the body of the P well, and both of them are connected to either the negative supply VSS or to the ground. Summary of CMOS fabrication process, you can have a look at. We have mask 1, which defines the area of P well. Mask 2, which defines the Thin-ox region where we need to form the P and N transistors. Mask 3 is used to pattern the polysilicon to form the gate. Mask 4 is a P plus mask in order to define the P diffusions. Mask 5 is again a P plus mask, but it is negative to the previous mask in order to define the N-type diffusions. Mask 6 is similar to our nMOS, only contact cuts are to be defined, which are to be exposed to the external world. Mask 7 is used to pattern the metal layer to make the connections. And mask 8, which is not discussed in the fabrication, but it will be used for overall passivation or overall glass layer to define the openings for access to the bonding pads. The lecture level practice problems for this topic can have a look at LLP 1 lecture level on outcome 1 based on illustrate the significance of photolithography. LLP2 emphasize the additional steps in CMOS fabrication compared to nMOS. Additional LLPs illustrate the significance of photoresist. Analyze how a CMOS transistor is better than an nMOS transistor. That's all for this topic. Thank you. Happy learning.